For ADC lab 3.1 ECE cycle 1 experiments. First one is amplitude modulation. And second experiment is a double sideband suppressor carrier. And third experiment is based on a spectrum analyzer. And the fourth one is pre-emphasis and de-emphasis. And fifth experiment is based on a sampling theorem verification. And sixth experiment is based on time division multiplexing. Okay, and here the very first experiment in the ADC lab first cycle is analyze and test AM modulation, modulation as well as the demodulation. In the name itself, the experiment, okay, and here we have to understand the basics of the modulation. So the main aim of this experiment is, okay, and the generation of the amplitude modulated wave. And in that, the important aspect is there are so many parameters, but here in this experiment, we are determining what is the percentage of modulation. And in this case, okay, we'll take different possibilities of the different cases like under modulation, over modulation, and all the things. And the second aspect in the same experiment is we have to verify demodulation of the modulated wave. And we have the different methods, and here in this we'll use the envelope detector method for demodulation. In this we'll verify whether we are recovering the original modulating signal or not. And in this, for this experiment, the apparatus required, or because we are constructing the circuit based on this apparatus like transistor, diode, resistor, with the specification transistor, okay, and because we are using the nonlinear device for the generation of the amplitude modulation. That's why we are using the transistor for this purpose. And diode is useful for the demodulation, and remaining resistors are useful for biasing, and capacitor and inductor combination that gives tank circuit in the collector side. And however, in the circuit diagram we'll verify the same thing. And CRO, it is meant for getting the display of all the waveforms. Function generator and for the generation of the modulated wave or AM signal. So there is a need of carrier signal and message signal, and we know the definition of the amplitude modulation. It is the process of changing the amplitude of the carrier signal in accordance with the instantaneous pulse of modulating signal. So there is a need to take two signals. One is a carrier signal and modulating signal, and we have to generate these signals using the function generator. And RPS, regulator power supply, for the nonlinear circuit like with the transistor, there is a need of bias. Okay, now for this purpose, there is a need of the regulator power supply. And for AM, and we know this is AM is a double sideband full carrier. So this is a theory related to this experiment. And in a record or any experiment, there is a need to know the theory behind this experiment or the particular technique. For amplitude modulation or double sideband full carrier, amplitude modulated signal VAM of t, that can be represented by AC into 1 plus Ka m of t into cos omega ct. We are varying the signal, amplitude of the carrier signal, and original carrier signal is Vc of t, it is AC cos omega ct. If there is no modulating signal, if m of t is equal to 0, we will get the same thing, AC cos omega ct. And if the measure signal is applied, okay, and amplitude is varying in accordance with the modulating signal. If the modulating signal is increasing, obviously total amplitude increases. If m of t decreases, amplitude decreases. So this is a VAM of t, but in the practical sense there is a need to know. So it is okay, and with this notation normally we will get the amplitudes in terms of AC, there is a carrier amplitude plus message signal amplitude or like this. But in practical situation there are some difficulties are there that I will explain. So now with this, the modulated waveform according to the theoretical representation, okay, and if I are assuming it is a message signal m of t, and carrier signal Vc of t like this. Okay, and here you can take it's the AM minus AM. And carrier signal is a high frequency signal. high frequency or low time period. And let the amplitude is a suffix c minus a suffix c. And based on these representations, the amplitude modulated signal that can be represented by amplitude modulated signal V AM of t. It's a double sideband full carrier, and here we have to place message signal on the top of the carrier signal like this. And here we'll get the waveform like this. Just to revise the concepts of amplitude modulated signal, here I am using. Always take the solid line representation is the waveform, remaining all are for reference. So here theoretically it may be represented as AC plus AM, it is AC minus AM or like this. But practically it is referred as A maximum. And only on the one side it is referred as actually it is AC minus AM. It is minus of AC plus AM, and this is called A minimum. And from that modulation index mu that can be calculated as A maximum minus A minimum divided by A maximum plus A minimum. It is the procedure adopted for practical calculations. Even it is in terms of carrier amplitude and message amplitude, but because of the gain calculations and all the things, it is preferred to calculate the modulation index with this formula. Mu is equal to A maximum minus A minimum by A maximum plus A minimum. Okay, because of the transistor or non-linear device, there is a change in the gain or there are some other issues. So that's why here modulation index is calculated with this formula. Diagram for the modulation and anything. Okay, now the circuit diagram for the amplitude modulated wave is like this. Okay, and here carrier signal is applied at the base side. And R1 and R2 are meant for biasing. And however, I will explain the same thing with the hardware. Only for theoretical or demonstration purpose I am using this. And message signal is applied at the emitter side. That's why it is called emitter modulation. And because of the nonlinear circuit with the combination of carrier signal and message signal, there are so many frequencies are generated. But what are the frequencies of the modulated signal? Only carrier frequency FC, FC plus FM, FC minus FM. Only to allow those frequencies will use the capacitor inductor or tank circuit. With that it will allow only AM modulated signal FC plus FM, FC, FC minus FM. And this is the AM signal. And here it is called emitter modulation, as we are applying the message signal in the emitter. For example, if the message signal is applied at the base, it is a base modulated. And if it is applied at the collector side, it is the collector modulation. But here we are using the emitter modulation. There are some difficulties with the emitter modulation. Okay, and here with the practical circuit we can observe the same thing. In continuation with that, the demodulated circuit is like this. We are all very much familiar about envelope detector. Okay, and this is the AM signal or modulated signal with the diode. Will take the positive off cycle, and after that, okay, and we can recover only the envelope based on the capacitor charging. And this R is meant for discharging. So with that we can get back our original signal. Okay, and here with this experiment, just for information here I am giving, we have to collect this data, like what is the modulating signal amplitude. VM is nothing but modulating signal amplitude. Okay, and the reason for taking this modulating signal amplitude is, as the amplitude varies, obviously there is a change in the maximum value, minimum value. And corresponding to every modulating signal amplitude, we have to measure maximum amplitude, minimum amplitude, so that we can calculate the modulation index. Like that, we have to take 2 or 3 readings for the representation of the modulation index to complete generation of the amplitude modulated wave. Power supply. Okay, and these internal connections, no need to do all this. Okay. So this is the circuit diagram that we are going to implement. Okay, and here we know this arrangement like transistor. Okay, carrier signal is applied at the base through RS, R1 and R2 resistors for biasing. For emitter, there is emitter resistance. From emitter resistance, we have to use the message signal. And from in the collector side, LC combination is there. And for power supply, we will use the VCC. Okay, the same arrangement is there here even in the board. And all the internal connections are completed. So that's why it is enough to do only applying the carrier signal and message signal. So this is a place where we can apply the carrier signal from the function generator, and from that RS, and it is directly connected to the base. No need to do all these internal connections. And similarly, these two resistors R1 and R2 are meant for biasing. Even these resistors are connected to the base internally. And toward the emitter side, RE is internally connected, and from RE we have to apply the message signal using function generator. And in the collector side, capacitor is internally connected, and we have to connect inductor to form the tank circuit. And however, the power supply pin is connected to both R1 as well as the capacitor, and we have to apply the power supply externally through regulator power supply RPS. And with that, okay, here at the collector side we can collect amplitude modulated wave. Amplitude modulated wave. Now I will explain the procedure for the connections, and after that we'll do the experiment. So here, because the carrier signal is carrier signal and message signal are required, so there is a need to take two function generators for the purpose of carrier signal, message signal, and the regulator power supply for the purpose of function generator. And I have set the frequency as 10 kHz. 10 kHz. And here we have to take output signal from these two pins, output from the red pin and ground pin. And here we have to set 10 kHz as well as the amplitude as a high voltage, high value for this carrier signal, because to avoid the overlapping and all the things. So here I am applying the same thing. We will observe the output waveform in CRO. So here to verify, okay, and what is the frequency of the signal as well as the amplitude of the signal in the CRO. So here we have to set the ground in the middle of the screen, and here we will get the carrier signal with the 10 kHz frequency. And to observe the waveform, okay, and here you have to change the time per division, and here I got 0.1 millisecond in the range. And amplitude, I can set amplitude, okay, and here amplitude with the volts per division, and that is in the 5 scale. And here the total range, total value is total number of pins are 1, 2, and half of this on the upper side and half of in the lower side, totally 3 units I can take, 3 units into 5 volts per division, totally 15 volts peak to peak. And time period, I can take time period by varying the position. I can say it's only one cycle, 1 unit. Okay, one complete positive cycle, one complete negative cycle. It's the 1 cycle into 0.1 millisecond. That gives the 10 kHz. 10 kHz. Okay, 1 unit into 0.1 millisecond. Time period is 0.1 millisecond, and corresponding frequency is 1 by 0.1 millisecond. It's the 10 kHz. So that is a carrier signal. That is a carrier signal 10 kHz that we have to apply at the input or the base of the transistor. Okay, and similarly we have to set for the modulating signal. Modulating signal with the function generator with the around 500 Hz. Which is the modulating signal is a low frequency, and amplitude is also in the same pattern, around 2 or 3 volts. Okay, and here we will observe the same thing even in this case, and output can be taken from red pin and ground pin, black color. And here you can observe the same thing in the same channel, because as I mentioned, amplitude is very low. So here I have to set the amplitude, and even time per division we have to change, because it's a low frequency and high time period. Now you can measure the amplitude. It is in the 0.5 volts per division. Earlier that is in the 5 volts per division. Now okay, I can change it into 1. Total peak to peak is around 2 into 1, or 2.1 into 2.2 into 1. It's a peak to peak value for modulating signal is 2.2 volts. And similarly the time period, it's a 2 units on the horizontal side. Time period 2 units into 1 millisecond. So time period is 2 millisecond, 2 into 1 millisecond per division. So that the time period is 2 milliseconds, and frequency is 1 by 2 milliseconds. It's a 500 Hz. by measuring the carrier signal and modulating signal. Now modulating signal, because 500 Hz is a modulating signal, and output of this function or function generator that is connected to the message point like this. That is in the emitter side according to our diagram. According to our diagram or circuit diagram, if the message signal is applied through RE to the emitter like this. And similarly, collectors. Okay, and after applying the message signal, we have to apply the carrier signal, and here we have to take from second function generator. Okay, and here, okay, and according to our circuit diagram, we have to form tune circuit, and for this purpose, we have to use the inductor, particularly with the value of 130 milliHz. So that's why we have to set with the inductance box 100 millihenries into 1 plus 10 millihenries into 3. That should be connected across the capacitor to form tune circuit. And after that, we have to apply the power about 12 volts. And here you can collect the output from the collector side. Collector that can be connected to this, and in parallel we have to measure modulating signal. Modulating signal. So modulating signal is connected to the second channel of the CRO. And to observe these two waveforms, use dual mode. By applying modulating signal in the channel 2, so in the CRO we will get the display like this. So this is the modulating signal, and this is the modulated waveform. Modulated waveform, and to measure what is the maximum value and what is the minimum value. So modulated waveform is observed in the channel 1. So that's why I set its ground in the middle, so that okay, and we'll get the symmetrical waveform. And here you can observe the same thing. And from this waveform, you can see the peak value occurs at from the ground. You can see it is about 1.1 or like this. So now the A maximum value is 1.1 into volts per division 1. A maximum is 1.1 volts. And similarly, A minimum, that you can see A minimum that occurs at around 0.7, because every unit is divided into 5 parts. So subunit is 0.2 volts or 0.2 units. So here it is 0.7 units, 0.7 into 1. That's a 0.7. A maximum is equal to 1.1 volt and A minimum is 0.7 volt. So that we can calculate the minimum value, M value. So now I'm giving another information. If we are changing the amplitude of the modulating signal, so this is a modulating signal about 500 Hz. If you are changing the amplitude of the modulating signal, you can observe the same thing in the CRO, how it varies, the modulated waveform. Okay, this varies. So here I am varying the amplitude of the modulating signal, and you can observe there is a change in the A max and A minimum, because that's why here I have taken the modulating signal in the second channel. As the modulating signal amplitude varies, there is a change in the A maximum, A minimum. So if it is further increased, okay, and here you can observe, okay, and you can observe the complete overlapping of positive cycle and off cycle, and with that we'll get modulation index greater than 1. It's a over modulation. And here in the table, as I explained, here you have to take different possibilities. Okay, and here you have to measure what is the modulating signal amplitude. For this modulating signal amplitude, what is the E maximum, E minimum, and for that you have to calculate modulation index. In the second row, take another modulating signal amplitude. Now measure A maximum, A minimum, and calculate the modulating or modulation index. And with that, you can complete readings for different possibilities. And another important aspect is if we have changed the frequency of the modulating signal, the impact on modulated waveform. And here set it as a 500 Hz. If I change the frequency, okay, and here there is no impact on the modulated waveform because in AM wave, variation depends on the amplitude only. And here I am varying the frequency, and here there is no change in the amplitude. Okay, and here I am changing, and you can observe there is no change in the amplitude of the modulated signal. So even in this case, you can take different possibilities. Set as the frequency as 500 Hz, 600 Hz, and you can measure A maximum, A minimum. In either case, you will get the same values. And for demodulation, and for demodulation, okay, here the output of this modulated signal, or from the collector, you have to connect to the diode input, that is a AM input signal. And here you can measure a demodulated signal from, okay, you can observe the diode, resistor and capacitor. And here this is the output point where we can observe the output signal. So this is the output waveform, and you can observe the output. Okay, and now the channel 1 is meant for demodulated wave, and here you can measure the time period for this. And here it is around 2 units with the time bar division 1 millisecond. It is a 2 milliseconds time period as we applied earlier. And with that we'll get a frequency of 500 Hz only. It is a demodulation procedure. Even in this, just it is enough to measure what is the frequency of the demodulated signal and whether it is equal to the frequency of the modulating signal. These two are same, okay, and it is enough.